Welcome everybody to the Fractional Calculus Seminar Series. Today we have Professor Samriddhi Sankar, who is an associate professor at the International Center of Theoretical Sciences of the Tata Institute of Fundamental Research in Bangalore in India. Prior to this, Samriddhi obtained his PhD in physics at the Indian Institute of Science, ISC Bangalore, and then a short postdoc stint at the Observatory de Le Carte Azur in Nice, France. His research interests lie at the interface of statistical physics, applied mathematics, and computational fluid dynamics, focuses on high Reynolds number, a fully developed turbulence, and turbulence transport. He has also worked extensively on problem thermalization of finite dimensional ideal hydrodynamics, as well as most recently low Reynolds number bacterial suspensions. We are very happy to have you here. You may please begin your talk.
Thank you. Thank you, Pavan. Thank you, Arran, for the invitation. I have actually been sort of, benefited from your seminar series, often catching it on YouTube where you put these videos up. So thanks a lot for this. So my talk will, there'll be very little fractional in this, but I hope it might be of some interest to some of you. And partly because the question that we want to answer is an sort of old question in an even older field, namely turbulence. And in a nutshell, what we do want to solve is, how does the degree of chaos, and I sort of denote it by lambda, the Lyapunov exponent, how does it scale with the Reynolds number, and can we derive this result from the Navier-Stokes equation? So it's a sort of, fairly straightforward question. It's a question that, people have looked at in the past, of course. And what I hope to do in the next sort of 50 odd minutes is hopefully sort of shine a new perspective, a new light, if you like, on this rather old question. But before we get there, because it's not really a turbulence audience as such, let me sort of give a very brief introduction to classical turbulence. So essentially summarizing, let's say, Uriel Frisch's book in a few minutes. So turbulent flows are sort of ubiquitous. So you see them in their various avatars. And if one were to sort of, probably Benja would give us a better definition in an hour from now. But if you would like to think about it broadly, then it's the sort of complex, unpredictable, and essentially seemingly sort of random motion of fluids. And most of this sort of, like most things in classical physics, it often sort of the starting point is to ask the question, what is the velocity field u at position x and time t in a fluid? And, just to give you a little bit of context, of course, this sort of goes back to the work of Euler way back in the 1750s. And Euler wrote down his sort of famous equation, the Euler equation. The important thing here was that Euler dealt with what are known as ideal inviscid fluids. We'll come back a little bit to this by way of introduction. But as we know, real fluids have viscosity. And it took, another sort of, it depends on how you count it, of course, but another 70 to 100 years, let's say, for the final set of equations that we now know as the Navier-Stokes equations, which is essentially formally the Euler bit. But now you have, you're dealing with real fluids at the end of the day, and you have the notion of viscosity stuck in there in the sort of in the coefficient of kinematic viscosity, which attaches itself to the Laplacian of u. Now, the Euler equation, the Navier-Stokes equation, of course, sort of describes all sorts of flows. So what makes it turbulent? When are things sort of, and that's a million-dollar question, of course, but very naively, what one can do is essentially take ratios of the sort of linear dissipative term and the nonlinear term. You call them the Reynolds number after Osborne Reynolds. And then you sort of realize that in the sort of vanishing limit of this Reynolds number, flows are essentially laminar. And when this Reynolds number becomes exceedingly large, goes to infinity for convenience, flows become turbulent. And so, this is a nice illustration from Chirag's group, where, you see this blue dye in a flow. And if you look here, the Reynolds number is quoted. It's laminar up to a point. The blue dye looks just like a sort of, single line. And then as you crank up the Reynolds number, all hell breaks loose, and essentially the flow would be, for all practical purposes, what we would sort of consider turbulent. So, a revised sort of definition from what I did a moment ago would be that flows with very large Reynolds number are turbulent. Often, for convenience, we take them to be, infinitely large when we set up theory, and these sort of flows remain in non-equilibrium steady states. That's the convenient tool for statistical physicists, where the energy injected is on average balanced by the energy lost through dissipation. So essentially, this sort of leads to a definition for a theorist, if you like, which is that turbulence would be solutions of the Navier-Stokes equation at very large Reynolds numbers or small viscosity. So when I'm talking about turbulence, these are the solutions that I have in mind for from starting from the Navier-Stokes equation. So, it's of course it's a vast field, but just to sort of for the heck of completeness, let me sort of tell you a little bit in a minute or so that what are the sort of fingerprints of a turbulent flow that we look for. One of them is scale invariance. It comes with a question mark, and I think at your next talk you'll hear a little bit more and understand a little bit more why there's a question mark here. But essentially, it's sort of reasonably clear that if one were to measure the energy spectrum, which is defined here, then there are ranges of scales where it really doesn't matter where you're making the measurements, be it in the oceans, in the wind tunnel, on your computer, wherever the flow is turbulent and homogeneous and isotropic, away from boundaries, etc., you would get a range of scales which seem to follow this power law. It's k minus 5/3 for short. In reality, it's a little more than 5/3, and that comes about because turbulence admits what's known as intermittency. Let me sort of skip this bit a little because I think it should be covered in the next talk. And essentially, if you're not interested in actually measuring taking Fourier transforms of velocity field, taking the correlation functions, etc. But for example, in this very sort of fabulous paper in the early 2000s, about 25 years ago now, for example, if you measure the statistics of acceleration and construct the probability density function, and this is true for nearly all measurements that you can think of in turbulence, you find these sort of very big fat tails which are far from Gaussian, which make theory difficult. You can look at, for example, the dissipation statistics. So this is a plot of, suppose, you had an instrument, in our case, that's a computer, where you measure the dissipation in various regions in the flow. You will see that they're all over the place, and things are essentially intermittent, things are multifractal, and the question mark remains whether there is finite time blow-up. The other thing, and this is just for people slightly away from turbulence, which many of us find fascinating, are that these solutions of turbulence admit something which is known as dissipative anomaly, which is something which doesn't make sense, to put it mildly. In Newtonian physics, if you take away friction, there is no energy loss, there is no dissipation. But it turns out that unlike common sense, in turbulence, as you crank up the Reynolds number, push viscosity to zero, common sense fails. That's because we see that the dissipation rate goes to a finite positive value. So the problem we want to solve in this sort of turbulent flow, which has all these sort of exotic properties of multifractal behavior, intermittent behavior, scale invariance, dissipative anomaly, etc., is, again, just to come back to where we started, is to understand how the degree of chaos, the Lyapunov, scales with Reynolds number. Essentially, what is alpha? It scales with Reynolds, but what bar of Reynolds? So what we will do here, I mean, there are various approaches to sort of look at this problem. What we'll do here is borrow certain ideas that were recently developed by, by many people, including some of us in Bangalore, is this idea of decorrelators, and this was developed largely in condensed matter physics to understand chaos, transport, ergodicity, etc. And we'll try to sort of look at this, answer this question in that sort of with that formalism. So where do these ideas stem from? So just for completeness and for historical accuracy, this sort of these ideas were sparked about 10 odd years ago through this paper by Maldacena, Shankar, and Stanford, who sort of looked at a bound on chaos, that was the title of their paper, for essentially quantum systems. And what they found through the use of commutators, which is the natural sort of language in quantum mechanics, was the fact that the largest Lyapunov exponent scales linearly with temperature. We'll get to that in a second, but first one has to understand how do we think about these sort of probes, and I'm sort of being vague here a little bit because it sort of takes us down a rabbit hole. But the first sort of question is, can we sort of think about the analog of these measurements for classical systems? Essentially, what it means is, can I go from a commutator language to a Poisson bracket language? So I'll explain this rather simply through the following sort of short example, which will set us up for turbulence and Euler and Navier-Stokes. And this was work that many of us did 7 years ago, and this is in sort of setting up the problem in the language of the classical Heisenberg spin chain at infinite temperature. So essentially, this sort of obeys a nearest neighbor ferromagnet Hamiltonian with a certain spin precession dynamics. You can ignore those details, but what essentially you're talking about is a lattice of spins, which all have, size 1, essentially. But because it's at high temperature, they're not in any ordered phase, so each spin points happily in whichever direction it wants to. So what we do here, the sort of the analog of the OTOC is essentially the following. We generate random spin configurations, a Gibbs ensemble, and this will come back to bite us later. And what we do is we make two copies, absolutely identical copies of two spin chains, except, and we call them system A and B, except at t equal to 0, we make sure that one of these spins is rotated, right? So they are identical, except let's say choose a hypothetical origin here. So you make a copy of A into B, but you take this one spin and you just rotate it by a little amount. And then you allowed the systems to independently evolve. So as you independently evolve, you can measure what we are going to do soon in hydrodynamics. You can measure what you would call a decorrelator. Essentially, you want to see how soon the two systems A and B completely decorrelate. So the fact that at initially one of the spins was slightly different between the two systems, in time, this information travels across the spin chain, and at some finite time, the two sort of systems are completely independent of each other. So when you measure this, what you get in X and T is this sort of light cone. So essentially, D being 0 means that things are completely correlated. D being order 1, and you can see this trivially from the equation that I've boxed here. D being 1 means that the spins have now decorrelated. So at t equal to 0, let me walk you through this. At t equal to 0, remember the spin at x equal to 0 was marginally changed. So that's why you have a red little color. In time, nearest neighbor Hamiltonian, the information spreads that, aha, there is a difference between the two of us. And so slowly in a light cone, so it has a ballistic, it has a butterfly speed and all of that, this message travels. So this sort of gives us a window to develop a diagnostic in terms of this. This is not completely new for classical sort of nonlinear systems. Of course, people sort of look at it in other languages such as uncertainty, etc. But this sort of gives us a window into understanding how to develop a probe more generally. And this window also tells us that perhaps we can adapt these ideas within the framework of hydrodynamics and sort of, to begin with, get the analog of what's in yellow here for classical many-body systems. What is the bound on the Lyapunov exponent? Is it still linear in T or is it something else? So that's where, we begin our journey. And in like for many things in life, we begin with the Euler equation. All right. So the question is how to find a right model which is Hamiltonian. After all, once we come to Navier-Stokes, we will relax the Hamiltonian prescription. But I want to think in terms of temperature first. I want to still first address the question of in classical chaotic systems, is there a similar bound like the Shankar-Maldacena-Stanford bound for the Lyapunov exponent? So the temptation, of course, is to deal with turbulence, because that we know is sort of the most well-known example of chaotic systems. The problem is that turbulence is driven dissipative. It lacks the Hamiltonian structure, and thermodynamic variables are hard to figure out in that case. So the way out of this, we come back to this question in a bit, but the way out of this is to look for variations of the Navier-Stokes equation, which might retain a Hamiltonian structure, which is code word for energy conservation, and allow for statistical equilibria. And the way out is in the world of what are known as thermalized fluids. So what are thermalized fluids? So thermalized fluids is a simple prescription to do the following. So I can begin with either the one-dimensional Burger's equation or the three-dimensional Euler equations. It really doesn't matter. And then I construct this sort of Hermitian self-adjoint projector, the Galerkin projector, which projects the velocity field. This is these are partial differential equations, so they have infinite degrees of freedom in momenta. But now I project or I truncate my velocity fields so that they have a compact support in momenta. And so all the Fourier modes are bounded from above, let's say, by some finite truncation wave number kg. And so with that prescription, I end up with the Galerkin truncated inviscid equations, which is just sticking those projectors wherever I can in the partial differential equations. And these tend to show essentially chaotic solutions, but which are thermalized in a finite time and exactly what we want. They have energy equipartition, they have Gibbs distributions, and so they have this very strict notion of temperature from the point of view of classical thermodynamics. And this is an old field. This is not something that we invented. So it goes back to the work of T.D. Lee in the 50s. And then, this is a significant work by the Paris group of Sicholas et al., who showed exactly what's going on when you start to numerically simulate these Galerkin truncated equations. And in the 3D Euler equation, so let's ignore Burgers for a second. In the 3D Euler equation, what happens is if you measure the energy spectrum in time, as things thermalize, the energy spectrum develops a beautiful k-squared scaling. If you wait long enough, which I haven't shown here, essentially the whole spectrum becomes k-squared, nothing like your k minus 5/3 that Kolmogorov would have told you about. You'll find more of this of these details in this paper. And remarkably, you get these lovely Gibbsian distributions, the Gaussian curves. The different curves relate to different initial energy. Remember, energy is conserved. And so you can actually, from the variance of these curves, you can actually define temperature very well. All right. So all that we need to do to vary temperature in your numerical code or in the calculations, you just sort of change the amplitude of the initial condition, as simple as that. And so what you can then do is numerically solve, wait for a long time till you get a thermalized velocity field, which has all these beautiful Gaussian distributions, and your job is done. All right. So now the strategy is the following. We can take these thermalized solutions. Remember what we did with the spin system, made a copy one to the other, and we call system A what we had, and system B is equal to system A, but with a very, very, very tiny perturbation. You'll find all the details in this paper from some years ago. And then we can independently evolve systems A and B and measure point by point the difference of the two velocity fields. And what you see is the following. So this is an animation on a 2D slice from our 3D simulation of delta U. So at t equal to 0, it's blue. That means everywhere things are essentially 0, except this tiny dot where I've introduced the little perturbation given here. As time evolves, this perturbation starts to spread, and very soon delta U becomes non-negligible, and by this time, systems A and B have completely decorrelated. So we can measure this decorrelator, essentially take an average of delta U squared, then proceed, the technical details I'm skipping, but it's possible to sort of kill the R dependence by an overall integral on the domain. After all, we are interested in the temporal growth. And then from here, for the Euler equation, simply because of its thermalized solutions, you can actually construct the linearized equation. This follows trivially, well, not trivially really, but this follows from the Euler equation. So essentially, you write down on a big piece of paper the Euler equation, label the variables with the letter A, write another set, label the variables with letter B, subtract the two, knowing that this is the initial condition for the equation of the subtracted field. And when you do that, after some labor, what you end up getting is an evolution equation for delta for this phi field. And that evolution equation essentially sandwiches the two delta U different components within the strain matrix. Keep in mind that we will see a very similar structure shortly for the Navier-Stokes. And that's why I'm sort of going through this calculation a little bit in some detail. Now you can diagonalize this matrix in the sort of basis of the eigenvectors of the strain rate matrix. That's sort of reasonably easy to do. And then what you find at the end of the day is that the evolution equation of this decorrelator reduces to this nice form where it sort of depends on it's minus the eigenvalue in the compressional direction and phi. So you immediately see this must have an exponential growth because it picks up the compressional eigenvalue, which is negative definite. And so when the dust settles, you can calculate the full solution of this, and you find that at short times, the decorrelator grows as exponential lambda t, where lambda has this form, which is, if you ignore the degrees of freedom, which is square root temperature, in sort of contrast to the quantum bound, which is linear in t. So is all of this correct? So let me sort of go through the last bit and sort of don't worry about the intermediate steps. So the last bit is, and one can play the same game in the Burger's equation where the analytical calculations, surprise, surprise, much easier. And what you end up getting, and here we plot from our numerical data for both the Euler and the Burger simulations, the log of the Lyapunov exponent versus the log of temperature, and you find that it fits beautifully the square root temperature dependence that our theory predicts. So this is all very well, but that's not the problem that we want to solve, right? The problem, again, that we want to solve, let me remind you, is this question. This is with Reynolds number. Can we do it? And here we do not have the advantage of a Hamiltonian structure because by definition, this is driven dissipative, this is non-Hamiltonian. and I really won't be talking about this, but some of these ideas were tested in a very different context by our group for bacterial suspensions. If you're interested in sort of physics of living matter, this might be a nice reference for you to look at. All right. So, this work, I can summarize the result in one line, and those of you who know turbulence might be surprised with this result. But it means sort of say this work has been done by a whole bunch of students. Oiko actually is no longer here, but he's now in Oxford. He was my master's student. He's now in Oxford doing his PhD with Alex Shekoshihin. Ritik will be graduating, finishing his PhD in a couple of months, I think. Sugan is a postdoc now at Johns Hopkins, former student of mine, and Shubhra is my condensed matter colleague at ICTS, from whom I learned this business of OTOCs and their classical classical analogues. So the answer to this question, and we can sort of close shop right now, is the following: that we find the Lyapunov scales as Reynolds to the power alpha, where alpha is 0.59 plus minus 0.0. All right? And we'll now sort of go through a similar calculation to see where this sort of number can come from, and can we sort of see this in a meaningful way theoretically. So I'll just pause here to sort of check, because it's a Zoom meeting, to check if there are any questions where I will be sort of happy to take. In case things get completely confused. Okay.
Wait, so, I have a question.
Berenger, yes.
I'm not sure, you went a little bit fast, but the strain matrix from which you compute the eigenvalues, yes. It's the thermalized.
That's right.
But the thermalized state is very irregular. So how do you compute the strain matrix?
So what it's very irregular, but you can, but one is able to still think in terms of the strain rate matrix. So this is, one can still solve this problem, right?
No, this I understand, but how do you compute a derivative of VTH, of thermalized V? Because it's very irregular, right? It's not even...
Yeah, sure.
It's derivable nowhere. So how do you...
Exactly. It's very irregular. But what we are able to do is we don't need to directly solve this numerically, if that's what your question is, right? So this is the point. The point is that because this object that we find from our DNS, but just by doing the twin simulations, that is absolutely trivial.
This I understood.
Yeah. So what we are able to do is, now, because this is exponential lambda t, all right, we are able to sort of understand, and if you see, it comes with a minus sign.
Yeah.
So I have my three components, lambda, sort of two positives roughly, and one negative.
Yeah.
And so you can sort of see that the dominant contribution must be coming from the compressional direction.
Okay, yeah, this is okay.
All right. And so we sort of are able to reduce this equation to something where we see that this must be exponential. That's the point of this calculation.
Okay. But you don't diagonalize you don't do it numerically or something.
No. This is completely
okay.
And then the numerics are these twin simulations.
Yeah. Okay.
But there is a subtlety here. Maybe, Benji, after your talk, I can discuss this also with you.
Okay.
Over email at some point. But there are nice games that you can play with the strain matrix itself.
Okay.
Yeah. Okay. So
thank you.
Yeah. Perfect. All right. In burgers, as you can imagine, this question is easier to solve, because you can explicitly integrate the truncated
this I understand,
equation, because it's in 1D.
Sure.
And there you get the full expression with the constant in front and everything. Okay, great. All right. So let's play this game here. So the strategy is roughly the same. The strategy is take the sort of Navier-Stokes equation. Now it's the Navier-Stokes equation. We drive it to a non-equilibrium steady state. So I identify that field as UNESS, where NESS is for non-equilibrium stationary states. The field is intermittent and multifractal, so sort of one can look around and sniff around the field, and it shows all the sort of signatures that we discussed for turbulence. So now what we do is the following. We now sort of make a copy, make a perturbation around the copy, and we are going to monitor essentially this difference field. All right, so we will independently evolve and monitor the difference field. So let's have a quick sort of numerical bird's eye view of what's going on here. So this is an animation of the perturbation. So at t equal to 0, you see that little sort of sun in the middle of our cube. That's where the perturbation is. Everywhere it's black. That's because delta U will be 0. And now everything starts to sort of move around. Things are non-local. And so you sort of essentially in time, the perturbation spreads, and at large time, at large times, you essentially get the whole field decorrelated. All right. So now we can sort of, compute essentially the phi of t versus t. And so this is a movie which runs in parallel. So I'm plotting the points phi t versus t. So you can see, and this is a semi-log plot here. So roughly at the same time, let's say, I guess this is roughly the same time, you see, yeah, it's roughly the same time. So you see we are still in the exponential phase. As the system, as the system fully decorrelates, this phi t will saturate to a value 2E0, where E0 is the sort of average kinetic energy in non-equilibrium steady state. Now, the reason it, of course, saturates to 2E0 is fairly straightforward. If I calculate the square of this, then if my dot, if the correlation between UA and UB vanish, that's when they're decorrelated, then all you're left with is the sum of kinetic energies of the two equations. It, of course, depends whether you've taken the half factor correctly or not. All right. So now we did this for various Reynolds numbers, which sort of which go between sort of, embarrassingly small to moderately large. And we find that, these decorrelators on semi-log plots show a very nice sort of clean exponential growth. And the question that one would like to ask, of course, is what is lambda, what's the functional form of lambda as far as the Reynolds number is concerned? All right. So, of course, this is not new, as I said. I mean, this is a problem that people have looked at in the past. And I've sort of, and there's also recent work from the group of Guido Buffetta in QG flows, etc. But I'm just sort of sticking mainly to the 3D, some of the 3D results. I mean, the rest you'll see at the bottom of my slides. But essentially, sort of, if you like, mean field ideas would suggest that the Lyapunov should scale as Reynolds to the power half, square root. Remember, we get Reynolds to the power 0.59. Multifractal sort of ideas, this is work by Crisanti and others from Italy, they sort of pegged it with 1 minus h, 1 plus h, where h is a Hilbert exponent, which will sort of come up in the next talk, I'm sure. And more recent numerical simulations by Arjun Berera and Ho sort of showed that this goes as Reynolds to the power 0.53. There are also sort of more recent calculations from the group of Vasilikos and others. If I have time, I'll probably discuss those at the end of my talk. All right. So now these are the earlier attempts, of course. So now what we do is we take this approach, and from the Navier-Stokes, we are able now to sort of, let me just move this window, yeah. From the Navier-Stokes, we are now able to write down, after taking, after considering the fact that the field is incompressible, etc. So the evolution equation actually reduces to this form. So at this stage, this is really an equality. So this.
I'm sorry, Samriddhi, isn't it some gradient missing in the formulation of beta H?
In the formulation of beta eta, yeah, sorry, there's a gradient missing. Thanks.
Okay, it's a gradient square, right?
Yeah.
Okay.
So hopefully the next ones will be clearer. Yeah. Okay. So the beta eta, you mean? That's right. Okay. Thanks. That's the typo. So now what we are able to show is the following. Now, given that we had seen that there is an exponential growth, that would mean that, so phi dot at short times, I won't be able to go through all the details, but for those of you interested, I can go through them later, or it's in the sort of appendix of the paper. This term really doesn't count for much. So at short times, phi dot is essentially beta s plus beta eta. And given the fact that we saw that there is an exponential growth here, it's reasonable to assume that phi dot is equal to lambda phi. And we just speculate at this stage, and that's what we'll sort of worry about in a second. Each of these sort of beta s and beta eta are also proportional to phi with exponents lambda s and lambda eta. All right, that's the speculation that we make. Now, Sij is, of course, as many of you know, is of course a highly non-Gaussian and fluctuating function. It's sort of a typical plot of the different components of Sij that I've done here. Sort of looks like this, exactly like the Porta et al. Acceleration statistics that you saw. But the good thing is that we've sort of reduced the problem to determining what lambda s and lambda eta are. So the first thing first, is this even valid? Now, the good thing is that we can test it on our numerics, right? So what we do is we sort of plot the, it's a sort of cumbersome plot, but this red is just phi dot over phi. This is sort of beta eta over phi, beta s over phi. It won't surprise you that beta eta over phi is negative, beta s over phi is positive, and really the sum of these two numbers gives you the effective plateau here. The short time plateau, again, just to remind you, will really be the value lambda that we are after. All right. So how do we sort of think about this theoretically? So the beta eta sort of goes as square root Reynolds. There's not a lot of mystery to that. There are many ways that you can sort of think about this. You can sort of use classical turbulence theory. And of course, we verify this numerically. So, in the interest of time, let me not go through why this is square root of Reynolds. The interesting new quantity is this animal. So here again, what we do is the following. We sort of split or rewrite this, and here there are successive approximations that will come in. The sort of detailed proof is a little long, but not very complicated, but I'll sort of argue the proof of this. So you can write this in terms of essentially the eigenvalue and the eigendirection. So these are my three eigendirections. This is at short times. So at short times, now, okay, so now the point is, let me just go back here 1 second. So exactly what we argued in for the case of the Euler equation, you see this beta s term comes with a negative sign. So that would mean that for this animal to be positive, somehow the compressional direction, for reasons that we really don't know, must be biased more preferentially over the other directions. So when we actually look at the distribution of Ni squared, the compressional, the N3 being the sort of compressional direction, we do see in the distribution that there is a preferential bias, and at large times, this bias actually vanishes. That's when things saturate. So if we account for this, and this is where, I won't be going through this, I just have another few minutes left, but we can sort of do a cumulant expansion of this whole mess. And what we find is that lambda s essentially reduces to the mean of gamma 3 and its standard deviation. So here we have a sort of reasonably compelling theoretical calculation that is certainly, needs to be tested against numerics, which I'll do in a second, where you find evidence that this lambda s should be sort of that the dominant contribution to lambda s would be a competition of gamma 3 and the standard deviation on gamma 3. So again, one can sort of show, and I'll give the numerical evidence in a bit, but one can go through the standard arguments and show that gamma 3 really will scale as square root Reynolds, and that's really what it does. But what about gamma 3? What about the standard deviation? So here we are stuck. Here we are stuck theoretically, except to say that let's assume this goes as Reynolds to the power alpha. In case alpha is greater than square root Reynolds, then this will be the dominant term, and hence I have my sort of the Reynolds number scaling of the Lyapunov exponent. So at this stage, this is all that we can say, that the Lyapunov goes as this, as square root Reynolds plus Reynolds alpha, depending on the value of alpha, whether it's greater than 0.5 or less than 0.5, either the mean field theory result wins, or you have something which is, faster than the mean field exponent. Okay, so this in a way sort of summarizes everything that we have. And what it says is the following. So here's a plot. So this is a dense plot. So let me go through this sort of slowly. So what we have, these bunch of data points are the Lyapunov exponent themselves, which were calculated, sorry. So one bunch of exponents come from the value of the plateau here. The second bunch of exponents, which I'm calling lambda DNS, really comes from the twin simulations, where we actually let the perturbation grow. We don't really care about what theory does, but just calculate, the initial movie, if you like. And we also plot the standard deviation of gamma 3. And we find a reasonable sort of, agreement of all these numbers. So sort of consistent with this picture, where all of these collapse on the Reynolds to the power 0.59. If you like the error bars, it's about 0.04 curve. And whereas, the mean gamma 3, just to confirm what we just said, the mean gamma 3 really goes very well with the square root Reynolds. And these, the bottom sort of x-axis and the left axis is really data from direct numerical simulations, both the ones that we run, as well as we extensively, I should have acknowledged that earlier, we also used the Johns Hopkins database a lot to construct these SIJs and all these sort of the little ingredients in the theory for which I don't need time evolution. The theory tells me what the time evolution should be. Likewise, we sort of make a similar calculation for the Goy shell model. The shell model, is a dynamical systems model for the Navier-Stokes. It's not really derived from the Navier-Stokes, but at the level of 2-point functions, it seems to do a remarkably good job as the Navier-Stokes. And most importantly, for the Goy shell model, as you can see, you can go up to Reynolds numbers, which are kind of unimaginable right now from DNSs. That's the sort of top x-axis, the Reynolds number, which we get in our Goy shell model simulations. So the whole lot of this sort of follows the Reynolds 0.59 scaling, which seems to give us some confidence that it's sort of quite robust. I should add just one point, Pavan, if I can just take a couple of minutes, and that one point is that the shell model by nature is local in its interactions, and that gives rise to various interesting features, which I'm not covering, but I'm just sort of flagging it in case any of you are sort of wondering or are interested in what locality does to these set of calculations. They don't show up in the sort of short time Reynolds number scaling, but they do show up in super short time power law scalings for shell models. But that's something that people in many body systems sort of argue when constructing such decorrelators for systems which have local interactions and non-local interactions. So let me sort of end with a summary and perspective. I actually wanted to also talk a little bit about multifractality, but then I saw the order, so I will just skip that, and we'll listen to Berenger on that issue. But let me sort of give a quick summary and a perspective. So what we've done is we've sort of used these ideas of decorrelators, which sort of comes from a completely different, so I've sort of added all the references, which comes from a completely different area of physics, where people manage to couple thermodynamic variables with the timescales of chaos. And this becomes very interesting because then you can even sort of think about more sort of basic questions in statistical physics, which have to do with ergodicity, timescales of equilibration, and even how you sort of think about transport coefficients and chaos. I mean, you can sort of dimensionally argue how you connect butterfly speeds and Lyapunovs, etc., with transport coefficients. So they are quite very interesting sort of field by themselves. So what we've done in this talk is the following. We sort of take these decorrelators and we apply this to the world of turbulence and hydrodynamics. We do it in small baby steps. First, we do it with thermalized fluids, which are essentially Hamiltonian in character. And because they're Hamiltonian in character, because I have a notion of an absolute equilibrium, I can think of temperatures, and they're chaotic, so I can think about a Lyapunov exponent, and I am able to sort of find the scaling of the Lyapunov exponent with temperature, and what we find is something which is square root in temperature. I can then sort of move a little further from the world of Hamiltonian and thermalized systems to the world of driven dissipative inertial turbulence. And there, what I find there, temperature goes out of the window, but there one is sort of very interested in what Lyapunov does vis-a-vis the Reynolds number. And what we find is that the Lyapunov exponent sort of scales with the Reynolds number, but at a power which is much is a matter of opinion, but it's certainly larger than the square root mean field result, or even the sort of theoretical results that Berera and Ho reported a few years ago from very similar calculations, numerical without the sort of theoretical stuff that we do to rationalize these ideas. And in a way, this sort of connects, if you like, intermittency to chaos. That's because we are able to sort of connect it with the fluctuations in gamma 3. Gamma 3 is so strongly fluctuating quantity, and that's what determines the leading order behavior of the linear of the Lyapunov exponent. When we look at more local models of turbulence, which are shell models, this is the point that I was making a minute or so ago. I'd forgotten that I actually kept it here in the conclusions. So if you look at more local models of turbulence, and these sort of relate to ideas here in the red part, what we find is that at very short times, you also get an initial power law growth, and that power law of growth quickly gives way to the exponential world. And finally, and this is what I didn't talk about, but now many of us sort of are in the business of biologically motivated questions. What you sort of what one can also do is to come up with similar ideas in active or bacterial low Reynolds number turbulence, where the picture is rather different from this sort of unbounded growth with Reynolds, but it really leads to maximal chaotic states, and there are critical sort of levels of bacterial activity where the system seem to be maximally chaotic, and that has its own implications in terms of mixing and other such questions. So, all right. So I will sort of stop here because, otherwise I don't really want to get into this business of are we surprised from the multifractal picture. I'll just stop here and take your questions. I'm sorry I may have overshot my time a wee bit. Thank you very much.
No, you're perfectly in time, so that's fine. So if you want to take extra 5
No,
minutes.
yeah, no. I mean, there are two talks, so let's take it easy.
Okay, fair enough. So for questions, please raise your hand. I'll call up your name in the order they appear on my screen.
So
I think Benajre has a question.
okay,
Please
sorry,
go ahead.
Yes, very nice talk, Samriddhi. In fact, I have two questions. Can I ask two questions, or do I ask one and then I wait?
No, you can ask two questions. That's
Yeah,
fine.
but I'll give very short answers, and then we can
Okay.
talk on email later.
First one, are you sure that it's a power law? Could it be a power law with a logarithmic correction?
For the you mean this one?
No, the 0.59.
Oh, you mean whether, yeah. So logarithmic corrections, yes. I wouldn't really hedge my bets on this.
Okay, so then I'll write to you later.
Yeah, perfect.
And
So
the
if you have a
second,
log correction to this, I'll be very happy to see it.
second question is about Vasilikos. So what about Vasilikos? What do you think about Vasilikos?
No, I mean, I saw the work, so we were in touch for earlier as well on this. So it's very nice. That's a very nice piece of work, as you know. And the interesting thing there is, as I was reading that paper some time back, Vasilikos sort of, also comments on the fact that the stronger than square root Reynolds, he doesn't rule out that possibility, as you remember. I don't know if you remember from his Reynolds exponent, similar to what Guido, etc., get for QSG, which is 0.6 or something. He sort of mentions that this might be coming from, and I hope I'm paraphrasing him correctly, coming from accounting for timescales which might come in because of streams, etc. So I think, as we do in our paper, we sort of mentioned that I think it's it's a very similar idea that they probably also had in sort of understanding where the stronger than Ruel or the old multifractal ideas sort of emerge here. So I think there is not much. No, I don't think there is any contradiction between these two set of results, Berenche.
Okay, because I look at Vasilikos' paper. I was not completely convinced about the power law.
Yeah, but that's a numerical observation. So that's a sort of, a sort of part that I sort of treat those two separately. So the numerical observation. So again, I mean, did you also think that there might be some log Reynolds somewhere hiding? Was that your?
No, it seemed to me that Vasilikos had two regimes, and I was wondering whether it's because because you have two power law, you could have a crossover.
Oh yeah, absolutely.
So at low Reynolds, you would more see one contribution, and at high Reynolds the other one.
Oh yeah. Crossover, yes. No, sorry. What I thought you meant was the fact that the standard problem you get when you have two power laws and which is the dominant one. So are you saying that there could be a crossover from one scaling to the other at a Reynolds number?
Yes, because you have a superposition of two Reynolds numbers. So
It depends on the coefficients. It depends on
the coefficient in front, but
the standard sort of, yes. So
and
we
in fact,
did
if you look
that.
at the result by Vasilikos, you seem to see a kind of crossover.
Right.
So I think your result is very nice because it would explain this.
Exactly. So we did look at that, Benja, and the bad part is, I mean, we actually don't even comment on that in our paper, but given my old ESS background, as you know, we did look at the dominant, subdominant, and crossover here. The embarrassing part is for this calculation. I'll send you the appendix, or you can see it on the archive, Benjay. For this calculation for gamma 3 standard deviation, we can't pin down the coefficient, the constant in front, completely accurately. So which makes
Okay, so
theoretically the competition between, let's say, C1 and C2 slightly involved.
Okay.
So, but it's worth sort of thinking about if we, I don't know, maybe we can get more data in Reynolds. As you see, I mean, the range of Reynolds that we have. And so we had to sort of resort to a GOI to extend it even more to see if it's robust or not, this calculation. And strangely, the GOI analytical calculation is far more complicated than the Navier-Stokes in this case.
Okay, thank you, Samriddhi.
Great,
I'll
thanks.
send you a mail about the low
Yeah,
code.
perfect, do that, perfect.
Are there more questions? You can unmute your mic and ask your question. Probably no.
Great.
Probably, I assume there's no further questions. Since you showed the experiment of Osborne Reynolds, I'm happy to mention that the original apparatus of Osborne Reynolds is preserved in very well condition at University of Manchester, and it's still in full working condition. So last when I was student, like a couple of years ago, it was I saw it actually
You've actually seen it.
working.
That's
Yeah.
fantastic. Yeah.
Yeah.
If you have a photograph, do send it to me. I can put them on my slide with your with credit to you when I give talks, which
Yeah,
are
sure.
for
So if I
general audience.
hop
Because I
over to
do
Manchester,
sometimes those
pick up,
experiments for,
yeah, yeah,
undergrad or whatever, high school kids talks.
yeah.
Okay,
Sure,
so
sure.
I'll stop sharing screen so that Berger can get on with
Okay,
more
okay. Thank
interesting
you very
labs.
much
I
again.
left the whole multifractal business for the next talk because she's the expert and not me.